Every enterprise today runs on fragmented data. Data is distributed by design. Your e-commerce data could be sitting on one of these Azure Data Lake storage. Customer profiles are Iceberg tables on AWS S3s. Product catalogs land in Google Cloud Storage in Delta or Iceberg format, whichever the team chooses. Microsoft Fabric Lakehouse holds your supply chain data. Snowflake runs your data warehouses for finance datasets. Databricks powers your ML workloads for analytics, and it will have data spread across Delta and Iceberg catalogs. Similarly, you could have Google BigQuery, you could have Synapse Analytics run serverless and dedicated data on demand, and you could also have you could also have Azure SQL databases serve your operational CRMs. That could be your SQL databases. Each system is purpose-built for its own domain, governed by its own team, secured by its own identity provider. And that's exactly how it should be. But here's the problem, and it's a huge moment. The moment an analyst needs to answer a question that spans two or more of these systems, say join a customer profile on S3 with order history in BigQuery and sales on Azure, the entire thing breaks down. Today the options are brutal. You build an ETL pipeline, you wait for access, you copy the data into a single warehouse, co-locate them. That takes weeks and creates a stale replica. You export CSVs and paste them together. No one should be doing that in 2026. Or you file a ticket with the platform team and wait for someone to wire up the connector on a shared Trino or a Dreamio cluster, which means shared credentials, shared access, and a governance nightmare. And there is a second gap. Even when analysts have access, they are staring at hundreds of tables across these systems, and meaning there is no intelligent layer that understands the semantic meaning of this data, help them reframe the right query across these sources. And that's where Unified Query Engine solves both of this problem. Let me show you how. Two fundamental design decisions set Unified Query Engine apart from each other. Federated query tool, each other federated query tool on the market. First, you bring your own credentials, your own service principal, their own access keys, their own personal token, no shared service accounts, no admin provisioning, no credential pooling. Two analysts querying the same storage account use their own independent identities. Access is governed by those who are, not by what the engine you're using. Second, every query is a clean room. Each query spins up an isolated compute session, authenticates only to the sources it touches, executes, results, returns the results, and tears the whole session down. Credentials are encrypted at rest, encrypted in transit, and destroyed after execution. There is zero state carried between queries, between users, between sessions. No other federated engine does both of these things. Trino, Dreamio, Starburst. They all require an admin to configure the shared connectors with shared credentials. Unified Query Engine is the first query engine built around identity scope per query isolation. And let me prove it how. To begin with, you could register. Let me just log in. It takes you to all your existing connections that you have created. This is the workspace, connections, and the object explorer on the left, a full-scale SQL query powered by Monaco in the center, and the results panel at the bottom. The results panel has the messages and history of all the queries that you've run. On screen, the foundation of everything is stored connection. I've already set up some connections across the data states. Let me walk you through what's here. So what you see here is a set of connections that have been created. To begin with, let me just show you the connections page. This takes you through all the diverse connections across cross clouds and all of these different diverse sources. Let me begin by having, let's say, an ADLS connection. You would point it to the storage. You would point it to the storage. You would point it to the container and all of your service IDs and authentication. And based on that, for each of them, similarly, from Fabric to Google Cloud, a AWS S3, SQL Server, BigQuery, Snowflake, Databricks, all of those. Now let's go back and see what I have already provisioned for all of these connections. I can browse any connection. The Object Explorer discovers the Delta tables or the Iceberg tables and the relational schemas, loads their column level metadata. The metadata becomes the foundation of both the SQL autocomplete, which means it is able to provide the intelligence to the autocomplete and the AI-powered querying, which we'll observe shortly. And the killer feature is the AI-powered feature, which we'll see shortly. Now let's begin with the first cross-querying. What you observe here in this query is a Databricks connection, which is an external Iceberg table on ADLS Gen 2, which is Azure Storage, Object Storage, and an S3 Iceberg powered Snowflake data. And we are going to cross query the customer data with the shipments detail to see what's the order ID that is actually shipped. And behind the scenes, the engine resolves each of these tables, stored connections, acquired the OAuth token, pulled the Snowflake credentials for Databricks as well, and each independently encrypted. It created isolated Spark session, registered each sources, and temp view executed the join, collected the results, and tore down the sessions. No credential persists on execution. Cross-cloud join executed in seconds. No data moved, no ETL, no shared credentials. And if you see, you have all the history of the queries that have run. You have the pool that it ran on, the rows it pulled, and the execution time. Now let's try to also understand a complete cross query that we will have between ADLS Gen 2, AWS S3, GCS, and all of the three joining across. Wow, so we just joined three clouds data. Let's try to look at an Azure SQL table. That was quick. Let's look at the Synapse Analytics, and this is an external Synapse Analytics table pointing to a Delta table stored on Azure Data Lake. That's great. Now I'd take you to a large data set. How does it work for a large data set? If you look at the count of this table, this is actually a sitting table on ADLS. And we have more than 100,000 records. Now, for those records which have more than 100,000 data, we can run a spill, which means for all of this data which is more than 100,000, it is then going to run a results for 100,000 records. Everything renders inline. But when the query returns 5 million or more, or even more than 100,000 records, you are fully powered to spill the data to your desired storage. In this case, we are going to spill it onto our storage account. The results panel switches in this case. You'd see server-side pagination. Each of the page would be streamed on Delta table using Apache Arrow, and you can see it has pulled 100,000 records, and you can see a pagination of 100 records, and it'll keep loading the data. At the same time, the queries run, you'd see a message that it's spilling the data onto the storage, and this is the path that it has spilled the data on. So let's go back, take a look. What do we see here on the ADLS? This is my storage. I have full permissions on this. You would find a unified query engine, the query ID, and a Delta table that it actually spilled on the data. That's great. Now let's look at let's look at a very large table, 100 million records. So what you see here, this is a 100 million record table, which is realistically a big one. And now let's try to do take a look at a predicate pushdown. There you go. So we have all of the predicate pushdown and pulled up the records. Now let me show you the second breakthrough. Analysts shouldn't have to memorize the table names across the tens of the data systems that they actually bring in and describe the query that they want to work with. First, I would pull up and show you the AI part of this integration. First of all, I would need to add one more connection to this, and that would be my AI. Let's define, and I would need to add the key. This is my Anthropic key. And let's add that. The moment you add this, you would notice on the right corner, there is a new Enable AI mode. This mode only comes up when you have an AI connection that has been added onto the connection object. So let's enable this. The moment we enable this, you would see a transformation. What happened? First, the workspace has transformed. The SQL editor now becomes a plain text input. The run button becomes the generate SQL, and a new AI SQL tab appears in the results panel. Notice the badge at the top. The badge at the top shows the number of tables that is available for context. The AI generates SQL grounded in real schema from the tables I have actually explored. No hallucinated table names, no guessing. Here's what's happening under the hood. When I have more than 30 tables explored, the engine runs a local embedding model entirely on the server, zero external API calls to rank each tables by semantic similarity to my prompt. Only the top 30 most relevant schemas get sent to Claude. This means a prompt like customer lifetime value by region will correctly surface the customer orders and region tables even if I have 200 tables explored across 5 cloud providers. Now let's take an example. I'm going to give a prompt and I'll ask AI to generate the SQL. Now what do you see here? The three things appear on the bottom on the AI SQL path. The generated SQL fully editable, a plain English explanation of what this query does and why, and a confidence which is color coded in green, yellow, or red. This is human in the loop by design. The AI proposes, you review, you edit it as needed, and when you're satisfied, you approve and run. And that's your query running. And that's your results. This is what it looks like when an analyst can go from question in their heads to an answer on screen across 10 data systems without writing a line of SQL and without moving a byte of data. Let me take a step back and frame what you have just seen. Every enterprise is multi-cloud. Every enterprise that has data governance, these two facts create every enterprise has data governance. These two facts create an impossible tension. Analysts need unified access, but governance demands isolated credentials. Today, the market offers two bad options: copy all your data into one warehouse, lose the governance, or keep it distributed and lose productivity. Unified Query Engine is that third option. Query data in place across any combinations of clouds and platforms with per user credentials and per query isolation, no data movement, no shared service accounts, no ETL. For technologists in the room, let me tell you how this is possible. Apache Spark is the powerful distributed data processing engine. It has the richest connector ecosystems across Data Lake, Apache Iceberg, JDBC, Parquet, BigQuery, Snowflake, Databricks, the most mature query optimizer and proven scale for petabyte. But Spark always has been oriented towards batch processing. You submit a job, it runs, it writes to storage. What I have done here is taken Spark Connect, a thin client gRPC protocol Apache introduced in Spark 3.4, and re-architected it into a multi-tenant interactive query engine with per user, per query credential isolation. Each query creates its own ephemeral Spark session over a gRPC connection to a shared Spark cluster. I built custom JVM side credential providers for Azure AWS S3, GCP, Snowflake, and Databricks that pull per user per session encrypted credentials from Redis at file system initialization time. The session registers each data source as a temp view, executes standard Spark SQL across all of them, collects the results, tears it down. The results of Spark operating as a live interactive multi-tenant query fabric and the sub-second session creation, per query credential scoping, and the full depth of Spark's optimizer and connector ecosystem underneath. That's a technical innovation at core. I took the most capable data engine available and made it behave like interactive query service without sacrificing isolation, security, or scale. What I showed you today is 10 different data sources across and unified into a query engine, and all of this on a single browser tab. It has server-side pagination and AI-powered natural language querying with semantic table ranking grounded in the real schema reviewed before execution. The data fragmentation problem is not going away, it's accelerating. Every new cloud service, every new governance boundary, every new team that picks their own platform makes this problem bigger. Unified Query Engine is built for that reality. Per user credential, per query isolation, 10 data sources, one SQL interface, zero data movement. That is Unified Query Engine. Thank you.